should look familiar from the last video. This was the bonding orbital determinant. Now, this was just for 2 electrons. What would happen if we had a large molecule? What would these determinants look like? Oh man, they would blow up. These terms would get more and more and more and more. We saw it was bad enough with a 3 by 3. So what did we finally come up with? We came up with a superposition of 2 determinants. So we'd have to calculate 2 determinants. And most of the molecular orbitals, once we finally boil that out, are going to be superpositions of different determinants. Now this becomes really complicated once you get up into multi-electron orbits of any size at all. So we have to come up with a different approach to this whole thing. All of this up to this point has lived in an area called a Hilbert space. And if we try to apply the fundamentals of the Hilbert space, we can do it this way. A tensor product of a Hilbert space of 1 electron and another 1 electron. So this ends up looking kind of like this. A vector 1, and this is a tensor product, which will double the dimension of this vector. So we end up with 4 vectors out of this tensor products, and all of these 4 vectors represent 4 different dimensions. The 4 dimensions, according to the Pauli principle, we should be able to swap 1 and 2 and get the negative sign. Now certainly these 1 and 1 and 2 and 2, that's not going to work for that property. But even for this one, it doesn't work. So we have to manufacture, if you want to call it that, a new state that does follow that property. And this demonstrates that Hilbert space has a lot of possibilities that we don't need. So let's come up with some tools that extract the correct states right from the very beginning. Okay, let's look at some tools that can build in these antisymmetric states. Here's the 1 electron Hilbert spaces with a tensor product. And the result of that is the symmetric projections of those Hilbert spaces and the antisymmetric wedge projections, which it would be considered a wedge product. And the wedge product is really the mastermind behind this. This is what we want out of this. Now this is not a tensor product, this is a direct addition. So all we do is include all of these things together. Not a tensor product, so keep that in mind. The symmetric projections for 2 electrons is this value, which is pp, where the p equals 1, 2. So that includes 1, 1, 2, 2, just like up here, 1, 1, 2, 2. And then the symmetric states, which are 1 over square root of 2, PQ plus QP, where P is less than Q. So we've only got 1, 2 to deal with, so that means 1, 2 plus 2, 1. Now notice, you switch 1 and 2 around, switch Q and P around, you don't get any sign change. So none of these are actually needed. And if we just want to count dimensions, there's only 1 dimension here. 1 dimension beyond that. Up here, there's 2 plus 1. So this is 3 dimensions, and this is 1 dimension. 3 dimension, 1 dimension. Now, to get the idea a lot better understood, let's expand this to 3 electron orbitals. Here we go. This gets the whole idea. Once you see 3, then you can expand it to multiple orbitals. Here's p equals 1 to 3, so that gives us 1, 1, 2, 2, 3, 3, and that is take that set with, and this is the union symbol, take the union of this and this set, which is 1 over square root of 2, pq plus qp. So, as long as p is less than q in the first one, then it matches. Okay, here are the possibilities. 1, 2, 1, 3, 2, 3. So, 1, 2, 3, 4, 5, 6, 6 dimensions. And for the wedge product, we only get 3 dimensions left out of that. The combinations 1, 2, 1, 3, 2, 3. And that gives all of those. Notice no Slater determinants, no mish, no mash, no problem with that. I think we're ready now to describe Fock Space. It's an infinite space, but it's made up of all these little pieces. Now notice, this is not a tensor product. This is a direct sum. So all these pieces belong to that. Okay, now let's dissect what this thing is so we can actually figure it out. H, fancy H sub n equals, oh, look at this, wedge product to the nth power. That means we take the wedge product of a bunch of these h's. And this is lowercase h, so what is that all about? And this wedge product thing is a subset, which kind of like what we showed before, the different cases that don't apply and the antisymmetric cases that do, is a subset of the full H expansion. Now this is a tensor product, so we're taking tensor products of little h down here. Now it gets more involved. This little bitty h needs a lot of explanation. The h is defined as the one particle Hilbert space, but that doesn't mean it's one orbital, doesn't mean it's one electron, it doesn't mean that it's one orbital. What does it mean? It's the space of all single electron states. Electron states, not the number of electrons. Now let's look, go back to the integrable square functions here, which we did before. These are the spatial functions, and we've kind of talked about that, and that's psi of vector r, which means it could be all over the place. So there could be an infinite number of those if we wanted to, and each one of those orbitals, spatial orbitals, has an up or down spin space. So this part looks nice, this part not so nice. Now quantum chemistry limits this space so that we're not trying to conquer the universe. The H normally spans, and these fancy X's are spin orbitals. So we figure out how many spin orbitals it's going to span, and that's how we figure this out. The dimension of the H is capital M. For minimal basis hydrogen, the M is 4. Now, what's the dimension of the H? Well, that would, if we take N, what is N? How many N's do we have? Well, the N is going to be the number of electrons. So what does that mean? Okay, we've got 4 to the n, which would be 4 squared, which would be 16. Okay, well, what's the dimension of the wedge product? The wedge product is supposed to take a subset of these things that really become the Pauli allowed states. So what's this m over n? Well, m over n is the total number of combinations of n that you can come up out of these 4 dimensions. So what would that be? I think it ends up being 6, but let's test that out to be sure. So now I have a new definition for the Fock space. It is this C, which is the spin space, up or down, and then we have H, that's 1H, then we have the wedge product of 2 H's, then the wedge product of 3 H's, and this keeps going on. So we'll take a sector of this Fock space, and in most cases it's good for our minimal basis hydrogen will be this sector piece right here that's going to apply.